Hypersonic flight begins at Mach 5, but the true significance of this threshold is not speed alone. It marks the point where air itself changes behavior. At lower velocities, air acts like a predictable fluid. At hypersonic velocity, air becomes compressed, superheated, and partially ionized. This transforms flight from a problem of aerodynamics into a problem of extreme physics. Hypersonic missiles operate inside this regime, where heat, pressure, plasma, and structural stress interact simultaneously. They are not simply faster weapons. They are vehicles that exist at the boundary between atmospheric flight and space physics, and this is why they represent one of the most disruptive technological developments of the modern era. The word Mach does not describe speed directly. It describes a ratio, the velocity of an object divided by the local speed of sound. At sea level, sound travels at approximately 343 meters per second, or about 1,235 kilometers per hour. However, this value changes with altitude and temperature, meaning Mach numbers vary depending on atmospheric conditions. Mach 5 corresponds roughly to 6,175 kilometers per hour, Mach 10 to about 12,350 kilometers per hour, and Mach 20 approaches 24,700 kilometers per hour, which is close to orbital velocity. Hypersonic flight officially begins at Mach 5 because beyond this point, conventional aerodynamic models lose accuracy and new physical effects dominate vehicle behavior. At hypersonic speeds, three major phenomena appear simultaneously. The first is shockwave compression. Pressure waves cannot move ahead of the vehicle fast enough, forming a bow shock that traps energy near the surface. The second is extreme aerodynamic heating. As air molecules collide with the vehicle at several kilometers per second, kinetic energy converts directly into thermal energy. Engineers quantify this using the stagnation temperature equation, where temperature rises proportionally to the square Mach number. At Mach 7, surface temperatures can exceed 1,500 degrees Celsius, hotter than aluminum melts and hot enough to weaken titanium alloys. The third phenomenon is ionization. At these temperatures, oxygen and nitrogen molecules lose electrons, forming plasma. This plasma layer interferes with radio waves and sensors, creating what engineers call a plasma blackout. Hypersonic vehicles therefore operate in conditions similar to spacecraft during atmospheric re-entry, despite remaining within Earth's atmosphere. This is why hypersonic flight is fundamentally different from supersonic flight. Supersonic aircraft operate between Mach 1 and Mach 5 and remain within predictable aerodynamic regimes. Ballistic missiles leave the atmosphere entirely and follow gravity-determined trajectories. Hypersonic glide vehicles, however, remain inside the atmosphere while traveling between Mach 5 and Mach 20, retaining maneuverability throughout their flight. This combination of extreme speed and atmospheric control has never existed before in operational systems. Small aerodynamic changes at hypersonic velocity produce massive trajectory variations. At Mach 8, a 1-degree change in angle of attack can alter the flight path by several kilometers. This makes prediction mathematically complex and forces entirely new approaches to sensing and tracking. Speed itself is not the most transformative factor. Time is. At Mach 6, a vehicle travels 1 kilometer every 0.6 seconds. At Mach 10, that drops to roughly 0.3 seconds per kilometer. A distance of 1,000 kilometers can be crossed in under 10 minutes. Traditional detection and response systems were designed for longer timelines, often measured in tens of minutes. Hypersonic vehicles compress these windows dramatically, forcing reaction cycles to operate on timescales previously reserved for automated systems. This compression of time is one of the central reasons hypersonics are reshaping global defense architectures. At these velocities, air becomes less like a gas and more like a compressible energy barrier. Drag force increases with the square of velocity, while heat generation increases approximately with the cube of velocity. Doubling speed does not double heating, it increases it many times over. At Mach 10, surface heat flux can exceed 1,000 watts per square centimeter, comparable to spacecraft re-entry conditions. This makes material science the primary engineering challenge. Hypersonic vehicles must survive extreme thermal gradients, oxidation, vibration, and structural stress simultaneously. They rely on advanced materials such as carbon-carbon composites, ceramic matrix composites, ultra-high temperature ceramics, and ablative coatings. Every gram of material and every millimeter of thickness must be optimized for strength, heat resistance, and weight. Guidance is equally complex. Plasma surrounding the vehicle absorbs electromagnetic signals, weakening GPS and radio communication. Hypersonic systems therefore depend heavily on inertial navigation, predictive modeling, and increasingly AI-assisted control algorithms. Control surfaces behave differently at these speeds. A millimeter of fin deflection can generate enormous force, while excessive movement can cause structural failure. Flight computers operate at extremely high frequencies, adjusting surfaces hundreds or thousands of times per second. Human reaction speeds are far too slow for this regime, making autonomous control essential. There are two primary architectural approaches to hypersonic vehicles. Boost glide systems use rockets to accelerate to hypersonic speed and altitude before releasing a glide vehicle that travels unpowered through the atmosphere. Scramjet-powered systems use supersonic combustion ramjets, where incoming air remains supersonic as fuel is injected and ignited. Scramjets have no rotating compressors. Instead, the vehicle's forward motion compresses the air. Combustion occurs in milliseconds, with internal temperatures exceeding 2000 degrees Celsius. Scramjets only operate effectively above Mach 5, making them one of the most technically demanding propulsion systems ever developed. From a physics perspective, hypersonic vehicles complicate detection because they fly lower than ballistic trajectories, maneuver unpredictably, generate plasma signatures, and compress response timelines. Radar systems must distinguish a hot plasma envelope from atmospheric noise while tracking an object moving several kilometers per second. This introduces nonlinear variables into systems originally designed for predictable motion. As a result, hypersonics demand new sensor fusion techniques, advanced computing, and AI-assisted interpretation. Despite geopolitical narratives, the real competition in hypersonics is scientific. Every nation working on this technology faces the same constraints: heat management, structural integrity, navigation through plasma, and manufacturing precision. Progress depends on computational fluid dynamics, supercomputer simulations, advanced wind tunnels, additive manufacturing, and artificial intelligence-driven design optimization. Hypersonic development represents aerospace engineering pushed to its absolute limits. Looking forward, hypersonic technology will evolve beyond missiles. Researchers are already exploring reusable hypersonic platforms, space access hybrids, and global rapid transport concepts. Future systems may incorporate adaptive thermal skins, electromagnetic plasma control, self-healing materials, and AI-guided flight envelopes. Some designs blur the line between aircraft and spacecraft, potentially enabling vehicles that take off horizontally, reach Mach 15 in the upper atmosphere, and descend thousands of kilometers away without entering orbit. These concepts are actively modeled by aerospace agencies worldwide. Hypersonic technology is transformative not because of destruction, but because of physics. It collapses distance, compresses time, challenges existing sensing frameworks, and forces breakthroughs in material science and autonomous control. Just as jet engines replace propellers, hypersonics redefine what motion through Earth's atmosphere means. They represent a regime change, not an incremental upgrade. And here is the deeper truth. Hypersonic missiles are only the first visible application. The same physics will power future space planes. The same materials will enable orbital manufacturing. The same control algorithms will guide autonomous atmospheric vehicles. Hypersonics are not simply about weapons. They are about mastering extreme velocity inside Earth's atmosphere. Once humanity learns to control Mach 10 reliably, the planet becomes smaller, space becomes closer, and transportation itself begins to change. If you want to understand how future hypersonic vehicles could travel between continents in under an hour, how plasma control might eliminate reentry heat, and how artificial intelligence is already designing aircraft faster than humans ever could, subscribe and stay with the series. Because next, we explore how hypersonic physics is merging air, space, and AI into one continuous domain, and that future is far closer than most people realize.